Thank you. Thanks for your time today. I want to talk about where I think, or maybe speculate, we are going in terms of how we do proving for roll-up chains. Let me start by talking about the status quo. How does this work today? There are two general approaches to proving the outcome of a roll-up. The first one is optimistic proving, or you might also call it interactive proving. Interactive because it involves a multi-step protocol involving multiple parties who are making different claims about the execution. So it's a multi-party protocol, multi-step, and it involves some kind of time limits or timekeeping during which the parties have to make their moves in the protocol or else lose by default. It's very low cost because in the common case in an optimistic protocol, a party simply makes a claim, and if no one disputes that, then the claim is accepted. If there is a dispute between parties, that has some cost, but that cost can be covered from funds that are slashed from the loser, from the deposit of the loser in the protocol. So very low cost, and an ordinary node of a chain has the capacity to participate in the optimistic proving. The other approach is so-called ZK proving, and I put ZK in quotes because, of course, these methods are not really zero knowledge in practice typically. It's a non-interactive proving protocol where a single party posts a cryptographic proof of correctness. This will have much lower latency to complete the protocol compared to an optimistic protocol. In an optimistic protocol, the parties have to be given enough time so that they can make their moves in the protocol even if there is censorship on the settlement chain. Whereas the ZK proof typically has much lower latency. The algorithms involve some complex cryptography and mathematics, some complex software tools. And proving is relatively expensive and sometimes requires high-end hardware. And so this is generally more expensive but lower latency. And this is the status quo. You do one or you do the other. Now, I think we can, now these approaches both work, but they both face bug risk, meaning that if there's a bug in aspects of your system, your protocol can fail because of a proof system bug. So first, I want to talk about bug risk because I think the thing that we need for next generation proving is to be able to cope with bug risk. Okay, so first let me talk about what it is that we're proving when we prove the execution of a rollup. Fundamentally, what we're proving is the execution of a state transition function, which is some deterministic function that takes the current state and some inputs and produces a new state and some outputs. It's typically written in a high-level language or languages, and it gets compiled down to machine code or down to a proof system. So this is what you're proving. Fundamentally, you're proving the execution of a fixed state transition function of this type. Okay, so let's talk about bug risk. We want to be resilient against bugs. That is, we want it to be the case that if there's some bug in the prover, or if there's some bug in the code of our state transition function, which in practice is quite complex, typically often written by taking, say, an EVM node such as geth and then making modifications to it. We might also have bugs in the compiler or related tools that take the source code we wrote for our state transition function and compile it into some artifact that we use in proving. And so we want to be resilient against as many bugs of all of these types as we can. Okay, and I'm going to categorize the bugs into two types, safety bugs and liveness bugs. A safety bug is a bug that allows an incorrect result to be proven. And a liveness bug is a bug where some correct result is not provable, therefore typically implying that nothing at all is provable. And so your proof protocol is unable to terminate. A bug in any one of these components could lead to either a safety or liveness bug in the whole end-to-end proving system. And the fundamental challenge that I want to address in this talk is how to cope with these types of bugs, how to make proof systems that are resilient against them. Okay, so let's talk about the safeguards, excuse me, the safeguards that we have currently. With optimistic proving against a safety bug, we have this mechanism conventionally of Security Council intervention. That is that there is a security council of trusted parties who are chosen by governance, and they can act if an incorrect proof appears to be happening. Worst case, they'll discover after the proof that it wasn't sound. So ideally, the Security Council will pause the protocol in order to give time for chain governance to fix it. Although today, most chains actually allow the Security Council to directly modify the state of the chain. That's protection against a safety bug. Against a liveness bug, the protocol will be stuck. You won't be able to make progress. And so again, governance action would be needed to fix that. So Security Council here is an important part of this. So let me talk about some best practices for how Security Councils are selected and managed. It's generally a multi-sig of independent parties, and independence in all the senses of the term is important here. Typically, it's a high approval requirement, not something like 9 of 12 or 10 of 12 for an action of the Security Council. And a best practice is to have the members be elected by governance and to have the election be done using a system that provides proportional representation so that a supermajority of the Security Council members necessarily represents the votes of a supermajority of the community members. Now, these protocols typically have a time window for action by the Security Council. After the protocol verifies a proof, you wait for a time interval to see if the Security Council will intervene. How long should that interval be? Well, it needs to be long enough for the Security Council to do everything it needs to do. To be alerted that something might be wrong, to get the evidence, to deliberate, to discuss among the committee members, decide there is a bug and that something should be done about it, such as pausing the chain, then jointly sign a transaction to pause the chain, and then get that transaction included on the L1 chain, even if there's censorship of the L1 chain. And this censorship problem is one of the core challenges here. All right, so let's talk about censorship resistance of this mechanism. There are different ways to handle this. The bad way to handle it is just to ignore the possibility of censorship. Say we'll give the Security Council 6 hours, that seems like enough, and after a proof is done, we'll have 6 hours of time. That's not a good approach. A so-so approach is to say, well, we'll make the council action period equal to the maximum censorship time that we assume on the L1 chain. That's typically 7 days. And that adds 7 days to the worst case completion time. But best of all, the best approach is to actually build this notion of a Security Council action period into the core protocol and prove safety against some censorship threat model that your protocol already ideally has. If you do this, we've at least in the Arbitrum protocol integrated it in a way that adds about 1 day to the worst case completion time of the protocol. Okay, let's talk about protecting ZK proving. Against a liveness bug, the protocol is stuck and you need some governance action to fix it, just like with Optimistic. Against a safety bug, with a simple ZK proving mechanism, you have no remedy. You've proven an incorrect result, it's been accepted, it's done, and there's no way to fix it unless you change the protocol. So ZK has advantages, but a big disadvantage is that you don't have a way around safety bugs. Okay, now you could say, well, let's add a Security Council action period here. But if you do that, you're going to have to add a lot to the completion time, and you give away the main benefit of ZK proving, which is a very fast completion latency. So this is not a great solution. If you want to keep it non-interactive, you can add what we call a confirmation committee. So a confirmation committee, there are different ways to do it, but one approach would be to have a 3 of 5 committee that's chosen somehow by governance. The committee members execute the chain and sign the result. They execute the chain independently of the ZK mechanism, meaning that they don't verify a ZK proof or generate a ZK proof. They simply execute the state transition function themselves by compiling it and running it. And then they sign the result. They sign if their result of execution that they got locally agrees with what was proven. And then you say, well, the ZK proof will be accepted only if it's also endorsed by a majority of this committee. And ideally, you can also require an attestation by a member's trusted execution environment in addition to the member's signature. That makes it more difficult for the members to cheat, but also the member signature provides a way for the members to say stop if the TEE seems happy, but the member knows that something is wrong. So then you say an accepted proof is safe, then if you do this, if the ZK stack is safe, or if the TEEs are secure, or if the committee is majority honest. That's a much nicer guarantee than safety bug means you're dead. Okay, so an honest committee then will turn a ZK safety bug, that is a ZK proof of an incorrect result, gets turned into a liveness bug because the committee doesn't sign, and then the ZK proof won't be accepted, the protocol is stuck, and you can fix it by governance. Okay, so, but we can do better than either of those systems alone, right? So far, we have a optimistic protocol that has a Security Council backup, and we have a ZK protocol that has this confirmation committee backup. But let's actually talk about why use different things. Why have a Security Council in one case and a confirmation committee in the other case? In the first case, so what are the differences? The confirmation committee is faster because the TEEs and signing happen automatically. The TEE will automatically execute the chain, automatically generate its attestation. The committee member will be set up to automatically sign the result unless the owner of that TEE steps in to take deliberate action. So committee members can then withhold a signature if they're worried. The Security Council is better from a security standpoint because unlike the confirmation committee, where the members' keys are held on-chain, they have to be held on-chain because they're constantly signing. In the Security Council case, the Security Council almost never needs to sign anything. And so the council members can hold their keys off-chain and can hold them in a more secure way. It requires explicit action from the members for something to happen. It's not as fast, but then again, in an interactive protocol, you're already operating on a much slower time constant. Okay. So you optimize for latency when using ZK because that's the advantage of ZK. You optimize for security when using optimistic. And that's why you have different forms. The Security Council, which has a veto, versus the confirmation committee, which provides a positive action to confirm. Okay. But why not do both? Why not combine optimistic and ZK systems? The idea here is simply that we have a proof system where we will allow either an optimistic proof with Security Council or a ZK proof endorsed by the confirmation committee. And if either one of those is presented, then the protocol will accept it and move forward. So we can accept the ZK plus council proof immediately if it's offered, or alternatively, we can allow anyone to start the optimistic protocol, but once that protocol is started, it can be shortcut at any moment by posting a ZK proof. So now, if you have a liveness bug in one of the two paths, you can still go ahead and prove by the other path. If you have a safety bug in the optimistic prover or the ZK prover, well then an honest committee or a confirmation committee or an honest Security Council will block that path and turn that, and then you can still prove via the other path. So by combining them in this way, you get this combination which gives some better properties than you could get with either system alone. So let's talk about then what guarantees this provides. We can say that the chain is safe under these conditions. If the ZK prover is safe or the confirmation committee is majority honest, then this proof can be done. If either one is true, this means that the ZK branch will not be able to prove a false claim. If the ZK prover is safe, of course, it cannot prove a false claim. Or if the committee, confirmation committee, is majority honest, then the majority will withhold their signatures. And in either case, you'll be unable to prove a false result. By the other path, we need one of those two to be true so that the ZK path doesn't have a safety failure. In order to guarantee that the optimistic path doesn't have a safety failure, we need that the optimistic proving protocol is safe or that the Security Council will act if something goes wrong. And so under these conditions, as stated here, our combination protocol is safe. And so because of the backups on the two paths, this should provide a relatively strong guarantee. The requirements for liveness are sort of similar, that the chain is live, that is, it can make progress by doing a proof if it's safe and if the following hold. The chain is live if either one of the paths are live. The first path, the ZK path, you require that the ZK prover is live, meaning that the correct result can be ZK proven, and that the committee is majority honest, so that the confirmation committee will be willing to sign that correct result. Alternatively, you can achieve liveness by using the optimistic path. There you have liveness if the optimistic prover is live and if the Security Council is minority honest. So for example, if you have a 10 of 12 requirement for the Security Council to veto a result, then you need only 3 of 12 to be honest. Because if those 3 withhold their votes from a false veto, then the false veto won't be generated. So here, optimistic prover live and Security Council minority honest. And here again, you can see an advantage from a security standpoint of the Security Council approach where you wait and provide a period for a veto. So you get liveness if either path is live. Okay, so next steps here. These ideas are relatively recent development from our research team at Offchain Labs. Interestingly, this is similar to, although it differs in some respects, from a post that Vitalik put up, I believe last week, talking about multimodal proving system. So our next steps are first to write and publish a more detailed spec for the overall protocol that nails down some of the details that you want in a specification. Then to implement and test it and move to deployment. I predict it's not up to me. Arbitrum governance and updates are decided by the Arbitrum DAO, but I would predict it's likely that this will be available for Arbitrum chains before too much longer. This is definitely a direction that I think makes sense to develop the protocols. Thank you for your attention today. And if we do have a little bit of time, maybe for a question or two. Any questions? Okay, thank you.